Okay, in this screencast we'll continue with our proofs by contradiction. So let's say that we have a natural number a, and we also have a prime number p. P is a prime. And let's assume that p divides the square of a. Then the assumption is that p divides a. And we're not going to consider the trivial case that when a is a 0, right? So let's assume that a is greater than 0. So how do we prove it? So suppose that p divides a square, and we will assume toward a contradiction that p does not divide a. Okay, so we know by the fundamental theorem of arithmetic that since a is a natural number greater than 0, right? Well, actually greater than 1, because we assumed that we're trying to prove that p divides a, that a has a unique prime factorization. So in other words, there is a sequence of product of primes p1 through pk. Could be a 1 prime, because a could be a prime number. Such that their product is equal to a. So a squared is equal to this product of primes taken twice. Okay, and that's equal to the square of every prime number, prime factor of a. So p1 squared times p2 squared times all the way to pk squared. So let's write it out. So a is equal to p1 squared times all the way down to pk squared, and since p divides a, this is equal to some natural number m greater well, it's a natural, right, in n, and m is not going to be 1. It's going to be greater than 1. Okay, so well, that means that p must be one of those primes, right? That is the only way that p can divide this product of prime squares. What does that mean? That means that p divides a. But this is a contradiction. Okay, let's generalize this, and there's an easy, a relatively straightforward consequence or corollary, as they say in mathematics, to this proof that if a is a natural number, well, let's assume that it is not 0 and not 1, greater than 1, and p is prime, and if p divides a to some power of q, right, where q is greater than 1, then p divides a. And the structure of the proof will be the same, right? We can prove it by the same method of contradiction, basically saying that let's assume that p divides a to the cube but does not divide a, and then we can derive a contradiction by showing that p, as a matter of fact, has to be one of the prime factors of a. Okay, so let's generalize this and prove that for any q greater than 1, p to the power of 1 to the q, right, the qth root of p is not a rational number. Right, m is an n, and n is an n, not a rational number, and m over n, right? So we have to assume that we'll assume that m and n are relatively prime, and p is prime. So the qth root of p is not a rational number. Okay, so again, we can use a proof by contradiction. So we assume that m to the power of 1 over q is a rational number, where m and n reduced to their lowest terms, so they are relatively prime. So that means that p is equal to m to the q. We're going to raise both sides of that equation to the power of q. And well, that means that p divides m to the q. Okay, so by the argument given above, we conclude that p divides m. Okay, so since p divides m, and then m is equal to p times some natural number l. Right? L is a natural number. It's an n. Okay? So what's m to the q? Then let's work with that one of the equalities above. Right? Rewrite it. So let's this. Right? Let's rewrite this as p is equal to m to the q is going to be p to the q times l to the q, and remember that q is greater than 1, and right, divided by n to the q. So that means that n to the q is equal to p to the power of q minus 1 times lq. So what does that mean? Well, that means that p divides n to the q. So that means that p divides n, and p divides p divides n, okay, and p divides m. So they're not relatively prime, m and n. So hence the contradiction. So we this is the statement that we have just contradicted. Okay, let's grab some space. some white space and generalize this fact that we can avail ourselves now to essentially prove many statements. I mean, of the form that the square root of the qth root of p is not a rational number, right? So well, that means that now we can show that the square root of 2 is not a rational number, and the square root of 3 is not a rational number, and then the square root of 5 is not a rational number. So any square root of a prime number is not a rational number. So send me your comments and try to find errors in my arguments.